Hello everyone, in this video we will be talking about classical cryptography techniques. So when we think about this classical cryptography techniques, we will be basically studying about the historical methods of encryptions that laid the groundwork for modern information security. So before we dive into classical cryptography techniques, let's go through what is cryptography. So cryptography is a science of transforming readable information, which is referred as plain text, into unreadable font, or also referred here as ciphertext, to prevent unauthorized access to data or to the information. It ensures that only intended recipients can decode and read the original message. So why does it matter? Why cryptography matters? So secure communication is the one of the major roles of cryptography has been a vital since historical times, as it is fundamental to military operations, financial transactions, diplomacy, and everyday digital life. Without cryptography, sensitive information would be exposed to interception and misuse. So now we can move forward with classical cryptography. As I told you, classical cryptography refers to the historical foundation of the cryptographical techniques, which heavily relied on manual methods of substitution and transposition. So, mathematics as a field was not that developed during those days. So, they relied on simple mathematical techniques such as substitution and transposition, which will be discussed later on in detail, and how they are used. So understanding them is really essential and appreciate the modern encryption techniques. As I told you, cryptography, it's mainly of two types. Basically, they are pre-computer era and post-computer era. Say pre-computer era and computer-driven algorithm. So classical cryptographical techniques usually relies on manual letter manipulation, which are substitution and transposition. And modern computer cryptography techniques are computer-driven algorithms using complex mathematical operations, include systematic and asymmetric cryptography. Its use and powers SSL, TSL, AES, RSA, and everyday digital security cryptographic techniques. So one of the core techniques when it comes to classical cryptographies are substitution and transposition. So substitution here refers to the process in which each letter or group is replaced by another symbol or letter according to a fixed rule, whereas transposition here refers to rearranging the position of letters without changing the letters themselves. So let's talk about one of the earliest substitution ciphers, which is Caesar ciphers, used during the Roman Empire, or attributed to the Emperor Julius Caesar. So, as I told you, it's also one of the oldest ciphering techniques, and it's also known as shift cipher concept. So, in this Caesar ciphering technique, each letter in the plain text is shifted a fixed number of positions down the alphabet. For example, if we take a plain text or a letter or a sentence such as hello, so with a shift of three, just we're shifting this letter HELO by position of three. So if we shift them and alphabet wise, so we will come as cipher text as KHOOR. And of course, we are considering the fact that we are with the orders such as A0, B is 1, like that. So here, encryption and decryptions are mostly done, can be represented mathematically, such as x plus k mod 26. and where x is the original position and k is the amount shift position. Decryption is also like x minus k mod 26, where x is the letter position, as I told you, and k is the shift value. So one of the major things to note is that Caesar cipher has only 25 possible keys, making it trivially breakable by brute force attack. So as I told you, these kinds of classical techniques cannot be used in today's modern era because due to the presence of only 25 possible keys, it makes it vulnerable to brute force attacks. Next is monoalphabetic cipher, also referred as substitution cipher, or is a category of substitution cipher. So it's a generalization of the Caesar cipher, where each letter of the plain text is mapped to unique fixed letter of cipher text alphabet, but not necessarily by uniform shift. So the value of the key or by the position by shift may not be fixed. It can be decoded using a formula, or it can be used through a formula, so that it may not be easily decoded or decrypted. So here also there is an issue with this type of ciphering technique is frequency analysis vulnerability. So despite its large key space, the monoalphabetic cipher is vulnerable to frequency analysis. In English, letters such as E, T, A, and O appear most frequently in sentences. A hacker can match cipher letter frequencies to known frequent language frequency to reduce the substitution mapping, often breaking the cipher with as few as 600 characters of cipher text. So unless we use some different languages such as French, German, it becomes very easy for the hacker to uh, decode the original decode and decrypt the get the original text using this if we use this monoalphabetic cipher. Next we come across is polyalphabetic cipher. So it's a multi-alphabet substitution technique. So instead of just relying on substitution only one, we can substitute a group or many more than one letter. Like I told you, unlike monoalphabetic ciphers, we can use several different substitution alphabets, switching between them during encryption. This means that same plain text can map to different cipher text letters, defeating simple frequency analysis. So one of the examples of this polyalphabetic cipher is uh, Vignere cipher, the most famous alphabetic cipher, which is invented during the 16th century. Keyword determines which Caesar shift alphabet is applied to each letter. Keyword is repeated to match the length of the platext. So an example is given below here, such as the keyword is given here as key and platext is given as hello. So of course, so for this key equal to 10, e equal to 4, and y equal to 24, shifts apply cyclically to give us the cipher text RIJVS. So this is how like polyalphabetic ciphers are done and processed. So moving on, we come across Playfair cipher, which comes under the digraph substitution techniques. So it uses a digraph-based encryption system in which we encrypt pairs of letters, referred as digraphs, rather than single letters. This makes frequency analysis significantly harder since there are 676 possible diagrams versus only 26 single letters. It was developed during the 1854 by Charles Wheatstone and was used widely by British forces in World War One. So the techniques involve phi into phi matrix construction. So here a phi into phi grid is filled with a keyword, removing duplicates, followed by the remaining letters of the alphabet. And one thing to note is I and J share one cell. So The ciphering technique can be better understood if we go through its encryption rules. So if we look at the encryption rules, it's divided into like three different rules, such as same row, same column, rectangle. So same row here means that each letter is replaced by the letter immediately to its right. It's like wrapping around. And same column. So instead of the row, here we consider the character being replaced by the letter immediately below it. And third is the rectangular rule here, in which each letter is replaced by the letter in the same row but in other letters column. So when you're doing preparation, you split the plain text into digraphs. Insert X between repeated letters, paired with X if the last pair is incomplete. Moving forward, we now move on to the Hill cipher. So Hill cipher is a matrix-based encryption techniques introduced by Lester S. Hill in 1929. It was the first practical polygraphic cipher, the first to encrypt more than two symbols at once using linear algebra. So how it works? So in Hill cipher, we consider plain text letters which are converted into numerical values, and they are converted using the order A is equal to 0, B is equal to 1, like that, and grouped into vectors. Each vector is multiplied by an invertible key matrix, modulus 326, to produce ciphertext. The encryption formula for Hill cipher is given as C into K into P into mod 26, where K is the key matrix, P is the plain text vector, and C is the ciphertext vector. So for our understanding, we have taken an example of 2 into 2 matrix. The key matrix K and plain text H is here given as like this. So 3325 is the key matrix, whereas 78 is the plain text matrix. So if we calculate the using this formula, you will get result something as 21 2, which if we use this numbering scheme like a equal to 0, b equal to 1, you will get the text vc. So this is about the encryption process. So when it comes to decryption, it requires computing the modular inverse of the key matrix. The matrix must be invertible mod 26 for this to possible. So this is one of the common classical cipher techniques, such as Caesar ciphers, monoalphabetics, Vignere cipher, Playfair, and Hill cipher. So when we broadly look over them, we can compare them using these four metrics such as type, key space, unit encrypted, and main vulnerability. So Caesar cipher is a monoalphabetic, key space limited to 25 keys, single letter, and of course mean vulnerability is brute force. It is very trivial. It's like one of the weakest classical ciphering techniques. Monoalphabetics is substitution, 26 keys, single letter, and of course its mean vulnerability is frequency analysis. The real and some Wiener cipher, the classical cipher techniques becomes a little advanced, and it took some time for hackers or people to decode them. So it's a polyalphabetic type of cipher. Key space is large since we consider keyword. This is, you don't encrypt it as single letters, and the main vulnerability is Cass's key or the index of coincidence. For Playfair cipher, the type it's of course the digraph classical technique. Its key space was quite large since we're using matrix. It's encrypted using letter pairs. So main vulnerability is the digraph frequency analysis. And at last, we saw Hill cipher is a matrix or polygraphic type of ciphering technique. Key space is very large, and its unit encrypted is like n letter blocks they are encrypted using n-letter blocks. Main vulnerability is the known plaintext attack. So if the plaintext gets leaked from the one of the end, it becomes much easier for to decode. Each successive cipher addresses weakness in the previous one, demonstrating the interactive nature of the cryptographic evaluation. However, all classical ciphers ultimately fall to statistical or algebraic attacks given sufficient ciphertext. So one of the major things is that these ciphering techniques, even though they were getting advanced evolutions through ages, one of the major things is that these all ultimately fall to statistical or algebraic attacks given sufficient ciphertext. So as the mathematics as a whole got advanced, these ciphering texts lose their values as they were getting decrypted in a shorter time um, as they went. So in the modern era, we're using some highly advanced mathematical techniques which are random and there is a period at which like we call the ciphering period in which the systems calculate the probable time to decode a particular algorithms, and as soon as the period is up, the technique is replaced by some other algorithm to make sure that the data does not get decoded or leaked from one end. And with this we come to the conclusion. So before we conclude, there's a brief summarization for the classical techniques. So we have explored Caesar, monoalphabetic, Vignere, Playfair, and Hill ciphers, each representing a milestone in the time of development of encryption methodology from simple shift to matrix algebra. So they all have the unique strengths and unique weaknesses. But if we summarize them, the strengths will mostly be they are very simple to implement, historically effective, and foundational to cryptographic thinking. Weaknesses were um, such as vulnerable to frequency analysis, brute force, and known plaintext attacks. So basically, these were suitable in those days when we didn't have any complex computational or thinking power. But with the with the age of computers and AI, these are not suitable for modern security needs. And this classical techniques actually laid the road to modern cryptographical techniques because they played a key role in symmetric algorithms such as asymmetric encryption system or DES and all, and asymmetric systems such as RSA and ECC. So the core principle behind this algorithms were of course confusion and diffusion, which introduced classically remain central to modern cipher techniques or design. The study of cryptography is not merely historical. It trains a cryptanalytic mindset essential for evaluating and designing secure modern system. So with this, we come an end to this video. Hope you like this video. Thank you.